Welcome to physics. I wanted to start off today with a summary of where we have been so far in electrostatics and then transition into applications. So, we've talked about electrostatic force, electric field, electric potential, energy, and electric potential. Electrostatic force, our equation F equals KE Q1 Q2 over R squared, and that's the basic attraction and repulsion of the charged objects. Electric field, that's how much force there is per coulomb of charge, and in units, that's going to be newtons per coulomb. Up here on electrostatic force, your units are newtons. So you have an electric field anytime you have a charged object, because anytime another charged object is brought near to the initial charged object, it will experience forces. So if you take a balloon and you charge it by friction, and you bring anything else near that charged balloon, it will interact with that balloon. So the electric field is just the name for that region around the object where you will get an interaction of those charges. Electric potential energy. Energy associated with an object due to its position in an electric field. So if I have a charged object and I move it in an electric field, I may be doing work to store energy, or the field may be doing work. Using the analogy of gravity, if I take a tennis ball and I lift up that tennis ball, well, lifting up the tennis ball, I'm doing work, and as a result of lifting it up, my tennis ball has gravitational potential energy. If I take a charged object and I move it against an electric field, then I will do work on that charged object, and the energy it then has is called electric potential energy. On the tennis ball, if I drop a tennis ball, gravity does work on it to change that potential energy into kinetic energy. If I have a charged object in an electric field and I release it, the electrostatic force does work on the charged object to convert the electric potential energy into kinetic energy. Electric potential sometimes goes by different terms. And so electric potential you may see as the term electric potential, or sometimes just referred to as potential, or sometimes just referred to as voltage, and even sometimes as a potential difference. It all references the same thing, and that's how many joules you have per coulomb of charge, whether those joules are potential energy, whether those joules are joules of work being done. So think of joules per coulomb. In analogy on all these, our electrostatic force, the analogy to gravitation is the weight of an object. Each is a force in a respective field. Electric field, the analogy is gravity or a gravitational field. We know Earth's gravitational field strength is a negative 9.8 meters per second squared, or negative 9.8 newtons of force per kilogram of mass. An electric field will be a certain number of newtons of force per coulomb of charge. Electric potential energy. Well, our analogy is gravitational potential energy, which we had an equation to calculate, and that equation was an mgy. We didn't get into an equation for electric potential energy, but the idea follows exactly the gravitational potential energy. Mass is the substance affected by gravity. In electric potential energy, the substance is charged. In gravitational, gravity is the field. In electric, electric field is the field. In gravitational potential energy, you have y, that's a distance. In electric potential energy, we generally use that distance as just a d because it's not in a certain direction vertically. And so Q times E times D will calculate the electric potential energy, but it's just the energy associated with an object due to its position in whichever respective field. Now, when you get to electric potential, there is no analogy because in gravitation, we dealt with a single object at a time, so we didn't need to take it a step further. With charges, we deal with millions, billions, trillions of charges, so then we needed an energy per unit charge. So hopefully that kind of brings things together on our different concepts. Now, let's transition into the application of static discharge. When you have a static discharge, it doesn't matter if you are rubbing your feet across a carpet and then touching, say, a cat or a doorknob and getting a static discharge. So anything from that small, or pulling an article of clothing out of the dryer and seeing a static discharge, all the way up to a larger discharge of lightning. These are basically all the same thing. They're just different on the scale to which they are occurring. But you need the same basic ingredients to cause these to occur. You need, first of all, a buildup of charge, and then you need a discharge to occur. And we'll go into much more detail on both of these things. So we're going to focus a little bit more on the larger scale side, the lightning, but things are happening the same on smaller scale discharges also. Here's our situation. There is our brand new school building. Doesn't quite look like that yet, but that's what it is intended to look like when it is finished, and it is making very good progress. So let's talk about lightning and how does it form, and then exactly what it is. We talked about a second ago. The first thing we need is to build up charge. So first thing I want to do is put charge regions on our diagram over there. Let's say in our storm cloud overhead, we have some positive charges there, maybe some negative here, some positives over there. Well, first thing we need to figure out is exactly how these charge regions form. So, two different ways of explaining these. First of all, precipitation hypothesis. This deals basically with what a cloud is made of. And so here is my very simplistic outline of a cloud. In a cloud, you have three different things. You have water vapor, ice crystals, and water droplets. So I'm going to kind of distribute these around the cloud. If I was more artistic, I would draw them, but I'm not, so I'm going to write words. So there are different things in our cloud. These things are not all the same mass. Of these three things, your water vapor is the lowest mass. And because it is the lowest mass compared to the other two, it will generally tend to sift towards the top, and gravity will pull the heavier ice crystals and the water droplets to the bottom. So then in my diagram, I'm going to draw arrows to represent that vapor moving up towards the top. And then correspondingly, your ice crystals and your water droplets moving downward towards the bottom. In this process of movement, there is friction between these different substances, and friction causes a separation of charges. The end result then, in our cloud, the vapor tends to carry a positive charge. So the top of the cloud will tend to be positive. The ice and the water droplets tend to carry a negative charge. And so the bottom of a cloud will tend to have negative charges. And so then what you end up with is a region of negative charge and a region of positive charge. That explanation is something that is observed to happen in clouds, and that's called the precipitation hypothesis. Now, another process that is occurring that can also explain the separation of charges is called the convection hypothesis. This is a little bit larger scale. So then we have Earth and then a cloud. Use your imagination, that's a cloud. And then I'm going to draw the outer edge of the atmosphere. The atmosphere is plus or minus in the neighborhood of about 20 miles deep. So you have clouds somewhere immersed between there. If you think about a cloud is made of, as we just talked about, mostly things of water. That water has to get up there somehow. Well, that water is going to get up there because it rises from the earth. And so from the surface of the earth, you have warm, moist air. Hot air rises because it's less dense. That warm air can support more moisture, and so that moist air tends to move up, and when it gets high enough, as the temperature cools, it will condense out and form that cloud. Well, on the surface of the earth, you have wind. That's just basically the air moving, and as the air moves, it will naturally cause friction, which will cause separations of charges. So there are charge regions all over the place near the surface of the earth just because of the moving air. Well, the moisture, just like the vapor in the last hypothesis, tends to carry a positive charge with it. So this warm, moist air, as it rises to form the clouds, is naturally positive. And so I'm going to draw a bunch of positive charges there at the bottom of the cloud. That's one process that is going on, the rising moist air, and it tends to be positive. The second thing that's going on here is going on in the upper atmosphere, the ozone layer. The ozone basically protects us. The sun emits not only light, but all kinds of different things in the electromagnetic spectrum, including higher energy X-rays and gamma rays. Well, the ozone, made of oxygen, that oxygen gets ionized, and so that high energy radiation ionizes oxygen in the ozone layer. Well, ionizing means that energy is transferred and outer shell valence electrons are kicked out of the atom. So then as a result, in your upper atmosphere up there, you're going to get all kinds of pockets of charges. Now, we know that opposites attract each other, and because opposites attract, what we observe, the cloud is positive, negative charges are attracted down, causing the top of the cloud to become negative. These are two processes that we observe that are going on in clouds. The precipitation hypothesis, the circulation of vapor, ice, and droplets to result in regions of charges, and the convection hypothesis, the rising moist air, and then the charges being attracted down from the ozone layer. In the end, we don't fully understand everything that is going on with charges. There are a lot of processes. These are two of the major processes. So, if we go back to our original diagram, we have regions of charge drawn in the cloud there. Notice I have not drawn the top positive, the bottom negative, or vice versa, but I've just put pockets of charge there because that's realistic. You're going to have different processes that are going to result in just different pockets of charge. We have the charge regions in the cloud, positive and negative pockets distributed in various different places. Now, this will have an effect on the ground. You will either induce or polarize charges depending on the substance that is there. So I'm going to draw regions of charge down on the ground on our brand new school building. On the right side, we have positive charges in the cloud. That will induce or polarize a negative region down on the school building. Kind of in the middle, we have those negative charges. That's going to induce positive charges to form on the school building, on the flag, on the tower, etc. And then over on the left side, we have positive. That's going to induce a region of negative. So those charge regions on the ground formed by either polarization or induction. We have our charge regions built up. The second thing we said originally, after the charge regions were built up, is that you would have a discharge. So let's talk about the discharge. When you have enough charge built up, and we're going to put a number on enough charge built up here in just a second. If I draw a lightning bolt striking. I'm going to give us a little more space here. So I'm going to take our school building and I'm going to move it down a little bit. We have a lightning bolt that's striking. Well, lightning bolt is going to strike whatever is closest. And so then we might have a lightning bolt that strikes from the cloud out to the flagpole, because that's about the tallest thing in the picture. That's the discharge. Well, if we look inside of this lightning bolt, so imagine we could take a little section here of our lightning bolt and we could zoom in. So our zoomed in section of the lightning bolt would reveal what's happening in terms of the atoms. So our original cloud up here, this was a negative region. And our original flagpole down here, this was a positive region. Well, that positive and negative regions, those are going to set up an electric field. And so atoms that are inside, so I'm going to draw an atom. Very simplistically, it has a nucleus, which is positive. It has electrons, which are negative. That's an atom. I'm going to put atoms all over the place here in our lightning bolt and our region around there. Realistically, they would be in all kinds of different orientations, but you get the general idea. Now, those atoms would be affected by the electric field. The positive parts of the atoms would be attracted up towards the negative cloud, and so we would tug on the positives in an upward direction. We would also tug on the negative charges towards the positive region down on the flag. Now, when you have enough charge build up, then you tug so hard on those charges that you actually pull some of the outer shell electrons off of the atoms, and those electrons begin to flow. The rest of the atom is now positive or a positive ion, and it will begin to flow, and that's your discharge. That is a lightning bolt. This process of actually pulling them off is basically called ionizing the air. And that's what a lightning bolt is. A lightning bolt is an ionized column of air. In other words, it's a pathway for charges to flow once you have enough charge built up. How much is enough charge? Well, in the investigation the other day, you measured electric field values, but you didn't measure them in your typical newtons per coulomb. The simulation had you measure them in volts per meter, which is another comparable unit for electric field. Enough charge built up is basically when you have an electric field that is 30,000 volts per centimeter of distance. At that level, the atoms in the air will not be able to hold on to their outer valence shell electrons, and you will start to pull electrons off, and you get a charge flow, and that charge flow is a lightning bolt. Typically on a non-stormy day, there are about 300,000 volts of potential difference between the cloud and the ground. So there is a general tugging on the charges in the atoms all the time. When you have a storm, what happens is it's typically windy, you have a lot of moisture in the air, you get excessively large regions of charge that form in the clouds, which then induce or polarize charged regions on the ground until you get to the level of 30,000 volts per centimeter of distance. Well, think about it for a second. How long is a lightning bolt? Every centimeter of distance corresponds to 30,000 volts. So you have hundreds of thousands, millions or more volts of electric potential when you have a lightning bolt strike. So let's take a second to look at some numbers on lightning. General lightning bolt, 3 miles long. That's a lot of centimeters in 3 miles. Each centimeter is 30,000 volts. I'm going to skip down. Your lightning bolts, 100 million volts, just as a general ballpark number for a single lightning bolt. Within a lightning bolt, you have 3 or 4 strokes. And what a stroke is a charge exchange, whereby you have negative charges flowing in one direction, positive charges flowing in another direction. And so you have 3 or 4 discrete charge exchanges. Electric currents, which we haven't talked about yet, but we're getting ready to talk about. 20,000 amps. That's 20,000 coulombs flowing in each second. Peak power of a lightning bolt, 2 billion kilowatts. That's equivalent to the power output of a small nuclear power plant. And the typical duration of a lightning bolt, less than a second. Now, you may see the light actually illuminate for longer than that, but the time period of charge exchange is very, very short, typically less than a second. Now, hopefully that gives you some background and idea of exactly what lightning is. There are all kinds of applications and what if questions and what about lightning, and that's part of what I want you to explore. So, more on that in the investigation. Ponder physics.